Circle.
A circle is a simple shape of Euclidean geometry that is the set of all points in a plane that are at a given distance from a given point, the center. The distance between any of the points and the center is called the radius. It can also be defined as the locus of a point equidistant from a fixed point. A circle is a simple closed curve which divides the plane into two regions, an interior and an exterior. In everyday use, the term circle may be used interchangeably to refer to either the boundary of the figure, or to the whole figure including its interior. In strict technical usage, the circle is the former and the latter is called a disk. A circle can be defined as the curve traced out by a point that moves so that its distance from a given point is constant. A circle may also be defined as a special ellipse in which the two foci are coincident and the eccentricity is zero, or the two-dimensional shape enclosing the most area per unit perimeter, using calculus of variations.
Terminology.
Arc, any connected part of the circle. Center, the point equidistant from the points on the circle. Chord, a line segment whose endpoints lie on the circle. Circular sector, a region bounded by two radii and an arc line between the radii. Circular segment, a region, not containing the center, bounded by a chord and an arc lying between the chord's endpoints. Circumference, the length of one circuit along the circle. Diameter, a line segment whose endpoints lie on the circle and which passes through the center. Or the length of such a line segment, which is the largest distance between any 2 points on the circle. It is a special case of a chord, namely the longest chord, and it is twice the radius. Parsant, a coplanar straight line that does not touch the circle. Radius, a line segment joining the center of the circle to any point on the circle itself. Or the length of such a segment, which is half a diameter. Secant, an extended chord, a coplanar straight line cutting the circle at 2 points. Semicircle, a region bounded by a diameter and an arc line between the diameter's endpoints. It is a special case of a circular segment, namely the largest one. Tangent, a coplanar straight line that touches the circle at a single point.
History.
The word circle derives from the Greek kirkos, itself a metathesis of the Homeric Greek krikos, meaning hoop, or ring. The origins of the words circus and circuit are closely related. The circle has been known since before the beginning of recorded history. Natural circles would have been observed, such as the moon, sun, and a short plant stalk blowing in the wind on sand, which forms a circle shape in the sand. The circle is the basis for the wheel, which, with related inventions such as gears, makes much of modern machinery possible. In mathematics, the study of the circle has helped inspire the development of geometry, astronomy, and calculus. Early science, particularly geometry and astrology and astronomy, was connected to the divine for most medieval scholars, and many believed that there was something intrinsically divine, or perfect that could be found in circles. Some highlights in the history of the circle are 1700 BCE, the Rhine Papyrus gives a method to find the area of a circular field. The result corresponds to 256/81, 3.16049. As an approximate value of p. 300 BCE, Book 3 of Euclid's Elements deals with the properties of circles. In Plato's seventh letter there is a detailed definition and explanation of the circle. Plato explains the perfect circle, and how it is different from any drawing, words, definition or explanation. 1880 CE Lindemann proves that P is transcendental, effectively settling the millennial-old problem of squaring the circle.
Analytic results. Length of circumference.
The ratio of a circle's circumference to its diameter is pi, an irrational constant approximately equal to 3.14159264. Thus the length of the circumference c is related to the radius a and diameter d by.
Area enclosed.
As proved by Archimedes, the area enclosed by a circle is equal to that of a triangle whose base has the length of the circle's circumference and whose height equals the circle's radius, which comes to p multiplied by the radius squared. equivalently, denoting diameter by d. That is, approximately 79% of the circumscribing square, whose side is of length d. The circle is the plane curve enclosing the maximum area for a given arc length. This relates the circle to a problem in the calculus of variations, namely the isoperimetric inequality.
Equations. Cartesian coordinates.
In an xy Cartesian coordinate system, the circle with center coordinates, a, b, and radius r is the set of all points, x, y, such that this equation, also known as equation of the circle, follows from the Pythagorean theorem applied to any point on the circle. As shown in the diagram to the right, the radius is the hypotenuse of a right-angled triangle whose other sides are of length x, a and y. b. If the circle is centered at the origin, 0, 0, then the equation simplifies to. The equation can be written in parametric form using the trigonometric functions sine and cosine as, where t is a parametric variable in the range 0 to 2p, interpreted geometrically as the angle that the ray from a, b, to x, y, makes with the x-axis. An alternative parametrization of the circle is. In this parametrization, the ratio of t to a can be interpreted geometrically as the stereographic projection of the circle onto the line passing through the center parallel to the x-axis. In homogeneous coordinates, each conic section with equation of a circle is of the form. It can be proven that a conic section is a circle exactly when it contains, when extended to the complex projective plane, the points I, 1, I0, and J, 1, I0. These points are called the circular points at infinity.
Polar coordinates.
In polar coordinates, the equation of a circle is, where a is the radius of the circle, is the polar coordinate of a generic point on the circle, and is the polar coordinate of the center of the circle, that is, rho is the distance from the origin to the center of the circle, and ph is the anti-clockwise angle from the positive x-axis to the line connecting the origin to the center of the circle. For a circle centered at the origin, that is rho equals 0, this reduces to simply r equals a. When rho equals a, or when the origin lies on the circle, the equation becomes. In the general case, the equation can be solved for r, giving the solution with a minus sign in front of the square root giving the same curve.
Complex plane.
In the complex plane, a circle with a center at C and radius, r, has the equation. In parametric form this can be written. The slightly generalized equation for real P, Q and complex G is sometimes called a generalized circle. This becomes the above equation for a circle with, since not all generalized circles are actually circles, a generalized circle is either a true circle or a line.
Tangent lines.
The tangent line through a point P on the circle is perpendicular to the diameter passing through P. If P equals x1, y1, and the circle has center, a, b, and radius r, then the tangent line is perpendicular to the line from a, b, to x1, y1, so it has the form, x1, a, x plus, y1, b, y equals c. Evaluating at x1, y1, determines the value of c, and the result is that the equation of the tangent is, if y1, b, then the slope of this line is. This can also be found using implicit differentiation. When the center of the circle is at the origin, then the equation of the tangent line becomes, and its slope is.
Properties.
The circle is the shape with the largest area for a given length of perimeter. See isoperimetric inequality. The circle is a highly symmetric shape. Every line through the center forms a line of reflection symmetry, and it has rotational symmetry around the center for every angle. Its symmetry group is the orthogonal group O, 2, R. The group of rotations alone is the circle group T. All circles are similar. A circle's circumference and radius are proportional. the area enclosed and the square of its radius are proportional. The constants of proportionality are 2p and p, respectively. A circle's circumference and radius are proportional. The area enclosed and the square of its radius are proportional. The constants of proportionality are 2p and p, respectively. The circle which is centered at the origin with radius 1 is called the unit circle. Thought of as a great circle of the unit sphere, it becomes the Riemannian circle. Thought of as a great circle of the unit sphere, it becomes the Riemannian circle. Through any 3 points, not all on the same line, there lies a unique circle. In Cartesian coordinates, it is possible to give explicit formulae for the coordinates of the center of the circle and the radius in terms of the coordinates of the 3 given points. See circumcircle.
Chord.
Chords are equidistant from the center of a circle if and only if they are equal in length. The perpendicular bisector of a chord passes through the center of a circle. Equivalent statements stemming from the uniqueness of the perpendicular bisector are: a perpendicular line from the center of a circle bisects the chord. The line segment, circular segment, through the center bisecting a chord is perpendicular to the chord. A perpendicular line from the center of a circle bisects the chord. The line segment, circular segment, through the center bisecting a chord is perpendicular to the chord. If a central angle and an inscribed angle of a circle are subtended by the same chord and on the same side of the chord, then the central angle is twice the inscribed angle. If 2 angles are inscribed on the same chord and on the same side of the chord, then they are equal. If 2 angles are inscribed on the same chord and on opposite sides of the chord, then they are supplemental. For a cyclic quadrilateral, the exterior angle is equal to the interior opposite angle. For a cyclic quadrilateral, the exterior angle is equal to the interior opposite angle. An inscribed angle subtended by a diameter is a right angle. See Thales' theorem. The diameter is the longest chord of the circle. If the intersection of any 2 chords divides one chord into lengths A and B and divides the other chord into lengths C and D, then AB equals CD. If the intersection of any 2 perpendicular chords divides one chord into lengths A and B and divides the other chord into lengths C and D, then A2 plus B2 plus C2 plus D2 equals the square of the diameter. The sum of the squared lengths of any 2 chords intersecting at right angles at a given point is the same as that of any other 2 perpendicular chords intersecting at the same point, and is given by eta 2-4p2, where r is the circle's radius and p is the distance from the center point to the point of intersection. The distance from a point on the circle to a given chord times the diameter of the circle equals the product of the distances from the point to the ends of the chord P71.
Sagitta.
The sagitta, also known as the vezine, is a line segment drawn perpendicular to a chord, between the midpoint of that chord and the arc of the circle. Given the length y of a chord, and the length x of the sagitta, the Pythagorean theorem can be used to calculate the radius of the unique circle which will fit around the 2 lines. Another proof of this result which relies only on 2 chord properties given above is as follows. Given a chord of length y and with sagitta of length x, since the sagitta intersects the midpoint of the chord, we know it is part of a diameter of the circle. Since the diameter is twice the radius, the missing part of the diameter is 2r x in length. Using the fact that one part of one chord times the other part is equal to the same product taken along a chord intersecting the first chord, we find that 2r x equals y/2, 2. Solving for r, we find the required result.
Tangent.
A line drawn perpendicular to a radius through the end point of the radius lying on the circle is a tangent to the circle. A line drawn perpendicular to a tangent through the point of contact with the circle passes through the center of the circle. 2 tangents can always be drawn to a circle from any point outside the circle, and these tangents are equal in length. If a tangent at A and a tangent at B intersect at the exterior point P, then denoting the center as O, the angles BOA and BPA are supplementary. If AD is tangent to the circle at A and if AQ is a chord of the circle, then DAQ equals 1/2 arc, AQ.
Theorems.
The chord theorem states that if 2 chords, CD and EB, intersect at A, then CAX star equals EAXBA. If a tangent from an external point D meets the circle at C and a secant from the external point D meets the circle at G and E respectively, then DC2 equals DGXDE. Tangent-secant theorem: if two secants, DG and DE, also cut the circle at H and F respectively, then DHXDG equals DFXDE. Corollary of the tangent-secant theorem: the angle between a tangent and chord is equal to 1/2 the subtended angle on the opposite side of the chord, tangent-chord angle. If the angle subtended by the chord at the center is 90 degrees, then L equals R. 2, where L is the length of the chord and R is the radius of the circle. If 2 seconds are inscribed in the circle as shown at right, then the measurement of angle A is equal to 1/2 the difference of the measurements of the enclosed arcs, D and BC. This is the secant-secant theorem.
Inscribed angles.
An inscribed angle, examples are the blue and green angles in the figure, is exactly half the corresponding central angle, red. Hence, all inscribed angles that subtend the same arc, pink, are equal. Angles inscribed on the arc, brown, are supplementary. In particular, every inscribed angle that subtends a diameter is a right angle, since the central angle is 180 degrees.
Circle of Apollonius.
Apollonius of Perga showed that a circle may also be defined as the set of points in a plane having a constant ratio, other than 1, of distances to two fixed foci, A and B. The set of points where the distances are equal is the perpendicular bisector of A and B, a line. That circle is sometimes said to be drawn about 2 points. The proof is in 2 parts. First, one must prove that, given two foci A and B and a ratio of distances, any point P satisfying the ratio of distances must fall on a particular circle. Let C be another point, also satisfying the ratio and lying on segment AB. By the angle bisector theorem, the line segment PC will bisect the interior angle APB, since the segments are similar. Analogously, a line segment PD through some point D on AB extended bisects the corresponding exterior angle BPQ where Q is on AP extended. Since the interior and exterior angles sum to 180 degrees, the angle CPD is exactly 90 degrees, that is, a right angle. The set of points P such that angle CPD is a right angle forms a circle, of which CD is a diameter. Second, c. P15 for a proof that every point on the indicated circle satisfies the given ratio.
Cross ratios.
A closely related property of circles involves the geometry of the cross ratio of points in the complex plane. If A, B, and C are as above, then the circle of Apollonius for these 3 points is the collection of points P for which the absolute value of the cross ratio is equal to 1. Stated another way, P is a point on the circle of Apollonius if and only if the cross ratio is on the unit circle in the complex plane.
Generalized circles.
If C is the midpoint of the segment AB, then the collection of points P satisfying the Apollonius condition is not a circle, but rather a line. Thus, if A, B, and C are given distinct points in the plane, then the locus of points P satisfying the above equation is called a generalized circle. It may either be a true circle or a line. In this sense, a line is a generalized circle of infinite radius.
Circles inscribed in or circumscribed about other figures.
In every triangle a unique circle, called the incircle, can be inscribed such that it is tangent to each of the 3 sides of the triangle. About every triangle a unique circle, called the circumcircle, can be circumscribed such that it goes through each of the triangle's 3 vertices. A tangential polygon, such as a tangential quadrilateral, is any convex polygon within which a circle can be inscribed that is tangent to each side of the polygon. A cyclic polygon is any convex polygon about which a circle can be circumscribed, passing through each vertex. A well-studied example is the cyclic quadrilateral. A hypercycloid is a curve that is inscribed in a given circle by tracing a fixed point on a smaller circle that rolls within and tangent to the given circle.
Circle is limiting case of other figures.
The circle can be viewed as a limiting case of each of various other figures. A Cartesian oval is a set of points such that a weighted sum of the distances from any of its points to two fixed points, foci, is a constant. An ellipse is the case in which the weights are equal. A circle is an ellipse with an eccentricity of 0, meaning that the two foci coincide with each other as the center of the circle. A circle is also a different special case of a Cartesian oval in which one of the weights is 0. A superellipse has an equation of the form for positive a, b, and n. A supercircle has b equals a. A circle is the special case of a supercircle in which n equals 2. A Cassini oval is a set of points such that the product of the distances from any of its points to two fixed points is a constant. When the two fixed points coincide, a circle results. A curve of constant width is a figure whose width, defined as the perpendicular distance between two distinct parallel lines each intersecting its boundary in a single point, is the same regardless of the direction of those two parallel lines. The circle is the simplest example of the